Now I want to talk about steady state. When we have this simple two-gene regulatory network where X activates Y, and if you assume constant X, then Y reaches a steady state. Let us assume this P sub XY is 0.2 and PY is equal to 0.9 and X is constant. The protein concentration is always 10 micromolar and initial Y concentration is 0 micromolar. Then what is this Y of 1? Y of 1 is P sub XY times X of 0 from this equation plus P sub Y, Y of 0, which is 0.2 times X of 0 is 10, so 10 plus 0.9, which is P sub Y times 0. And we get 2 micromolar. How about Y of 2? P sub XY times X of 1 this time, and P sub Y times Y of 1, which is equal to 0.2 times 10, because X is constant, always 10, plus 0.9 times Y of 1, which is 2, right? This is Y of 1, which is 2, so we have 2 here. This is a 2, and this is 1.8, so we get 3.8 micromolar. How about Y of 3? Again, it's P sub XY, X times 2 plus PY times Y of 2, which is equal to 0.2 times 10 plus 0.9 times Y of 2 is this value, so that's 3.8. And if you do the calculation, you get 5.42, and so on. This term, which is production term, is 2 here. This term is also 2. This term is also 2. So we have a constant production. At each iteration, same amount of Y protein is produced by X. How about degradation? So we have a 0 value here. And basically this is telling us that we have this amount of protein, which is 0, and you multiply that by 0.9. So actually there's a 10% decrease. But since we have 0 here, you multiply that by 0.9 and you still get 0. How about here? This is your Y value and you multiply that by 0.9, which means that 90% will remain and 10% again will be removed or will be degraded. And what's 10% of 2? That's 0.2. Okay, so that's 0.2. Here, there's no degradation. Now we have 0.2 micromolar is degraded. How about here? You have 3.8, and what's the 10% of that? That is 0.38. So 0.38 micromolar is degraded. So what is happening? Production is always constant. We have 2, 2, 2, but degradation is different. The amount that is degraded will continue to increase until that value reaches 2. As the concentration increases, the amount of protein that is degraded also increases. So when the amount of protein that is produced and the amount of protein that is degraded becomes the same, we reach a steady state. Now I want to show mathematically why this steady state occurs. So we have again simple two-gene regulatory network equation, and let's start from Y of 1. So Y of 1 is Pxy times X of 0 plus Py times Y of 0 from this equation. And how about Y of 2? Y of 2 is Pxy X of 1 plus Py Y of 1, again from this equation. But since Y of 1, which is this value here, is equal to this, we can say this is equal to Pxy X of 1 plus Py times this value here, which is Pxy X of 0 plus Py Y of 0, which is a Pxy X of 1 plus Py Pxy X of 0 from here plus Py squared Y of 0. And how about Y of 3? So y of 3 is pxy x of 2 plus py y of 2, which is equal to pxy x of 2 plus py times y of 2, which is this expression. So basically you need to write that expression here. And what you get is pxy x of 2 plus py pxy x of 1. This, if you multiply this and this, you get this. And then plus py squared pxy x of 0. And lastly, py cubed. So if you multiply this by this, you get this times y of 0. So what is the pattern that we observe? When this number is 3, we have a 2 here, we have a 1 here, and 0 here. So it's like if you have an n here, then we have an n minus 1, n minus 2, and then you go up to 0. That's the pattern that we observe. Another thing that we observe is that, let's say we have this value 1 here. Okay, it's 1 times pxy. Then we have a pxy here, pxy here, pxy here. And we see py to the power of 0, py to the power of 1, which is this, and py to the power of 2. Again, if we have n here, this value is n minus 1. Basically, you have n minus 1, n minus 2, and then you go up to this value 0 here. These are the patterns that we observe for x terms. And finally, we have this y term. And you see that this number is same as this number, right? Sorry, this number. This is basically large n. This is what we have so far. So let me write down this y of n. And let me write this y of 0 term first. So we have py to the power of n minus 1, y of 0, plus, let me write all these x terms now. So one thing we notice is that every term has this p sub xy, right? So we can write that down here, multiplied by all these terms, right? So let us use this summation, and we have py, and the exponent goes from 0 to 1 up to n minus 1. So if you call this k, py to the power of k, then this k goes from 0 to n minus 1. Then this expression will cover all these components. Now, that should be multiplied by all these x terms here. The index goes from n minus 1 to 0. So the index decreases. If you say the index is n minus 1 minus k, then if k is 0, then this value becomes n minus 1, which is this. How about if k is 1? Then n minus 1 minus 1 is n minus 2, which is this value here. And the last one, how about if k is this last value, n minus 1? Then n minus 1, so this value, n minus 1 minus k, which is this value, right? n minus 1. So we have n minus 1, which is n minus 1 minus n plus 1, which is 0. So we have this 0 here. And we know that p sub y is less than 1, right? And greater than or equal to 0. Then what is this value? Y of infinity. This is p sub y to the power of infinity of y of 0. And we know that this p sub y is less than 1. So this value will be 0. How about this one? Geometric sum is defined like this. When we have a plus ar plus ar squared plus ar cubed plus and so on, then that is equal to sigma k goes from 0 to infinity, and we have ark here, which is equal to a over 1 minus r, for the absolute value of r is less than 1, which is our case. So what is this A and what is this R? A is, in this case, this expression here. But we are assuming that X protein concentration is constant. So let's call that concentration just large X. It's constant X. And what is this R? R is P sub Y. So the expression we have, this A over 1 minus R, which is this one, becomes large X over 1 minus P sub Y. This Y over infinity has the first term, which is 0, and there's a second term. It's now P sub xy, which is this term here, and the rest is x over 1 minus P sub y. That's a constant value, and this is steady state level.